there's another way to view the symmetric groups, but it requires techniques of linear algebra. So that'll be a requirement for this part. Now, we have S sub n, symmetric group on n letters. S sub n is a natural group action on the set 1 through n. So recall, if we have an element sigma in S sub n, call sigma a permutation, sigma is a bijection from the set 1 through n to itself. So sigma is a function. The way we define the group action, sigma acts on the label I by evaluation. So we just evaluate sigma at I. Now, to see we have a group action, first we have to show the identity element acts on labels just by the identity map. And that follows by definition. Then we want to show if we have a product of permutations, we act on the label I. The same as if we act on the label I by each permutation separately. That follows because our multiplication of permutations is just composition of functions. So we have a group action. How do we get linear algebra into the picture? If I'm working with S sub n, then I can consider the real vector space Rn or the complex vector space Cn. Let's stick to real vector spaces for here. Now, if we have a sigma in S sub n, that'll induce a linear transformation from Rn back into itself. We define the linear transformation as follows. So if I take the standard basis, E1 through En, we'll define T sub sigma on the linear combination here, just by leaving everything alone except we let sigma act on the label of each basis vector. This is linear, so I'll leave it to you to verify that it respects scalar multiplication and vector addition. Now, since we're using the standard basis, I can just consider T sub sigma to be a matrix. So what's the recipe for getting that matrix? What we do is, we're going to take our basis vectors, line them up along either the top or the bottom as labels. If I want to know the ith column of the matrix, we take T sub sigma and evaluate on the ith basis vector. Now, for our T sub sigma, we're just applying the sigma to the label. So our ith column is going to be E sub sigma I. Now, some things to note. First, each T sub sigma is going to be invertible. So you'll note what we're doing here, we're starting with an identity matrix, and then we're just going to permute the columns. So that means we have exactly 1, 1 in each row and column and zeros everywhere else. Now, if we try to put that matrix into row echelon form, we can get to the identity matrix just by doing row switches. So since our row echelon form is the identity matrix, our matrix is invertible. For an example, let's consider S3. S3 has 6 permutations, so we get 6 matrices. Note, in each matrix, there's a single 1 in each row and column and zeros elsewhere. If we take the determinant of each one, that's non-zero, so each is an invertible matrix. Okay, in fact, the determinants are equal to plus or minus 1. Now, how do we get these matrices? Okay, we apply our formula. So for instance, 1, 2, 1 goes to 2, 2 goes to 1, 3 goes to 3. So E1 goes to E2, E2 goes to E1, E3 goes to E3. If we check the 3 cycle 1, 2, 3, 1 goes to 2, 2 goes to 3, 3 goes to 1. So E1 goes to E2, E2 goes to E3, E3 goes to E1. Now, for more general properties, we can think of T as being a map from S sub n to GLNR. So GLNR is a set of invertible n by n matrices with real entries. It's a group. We don't show that here, but we note if I have a group on each side, we can ask if we have a homomorphism. The answer is yes. Okay, so it's stated like this. Now, to check that, we would want to show, okay, if I want these two to be equal, they have to be equal when we evaluate them on every vector. Now that's enough to check on each basis vector by linearity. So I want to show that this linear transformation on EI is equal to this linear transformation on EI also. But these are both equal to E sub sigma 1, sigma 2I. So homomorphism. Now, because we have a homomorphism, we can ask, what's the kernel? Here, the kernel is going to be the identity. So if you think about what our permutation does, it takes the identity matrix and shuffles the columns around. The only way I can shuffle the columns around and get the identity matrix is if I use the identity element. So the kernel is the identity. Now that says our map T is 1 to 1. So we can think of S sub n as a subgroup in our group of invertible matrices. Next, we can ask about the inverse of T sub sigma. Okay, our first guess is going to be correct. It's going to be T of sigma inverse. So we just use the homomorphism property and the fact that if I want to find the inverse of T sub sigma, I just find another matrix such that when we multiply, we get the identity matrix out. So the homomorphism property says, okay, we lump together sigma with sigma inverse, we get the identity, and then we get the identity matrix. So this formula holds. Now, in the example we saw, determinant of T sub sigma was plus minus 1. That holds in general, so why? If you note from the previous board, well, we were able to show that T sub sigma was invertible by going to row echelon form, which was the identity matrix. Now I was able to go from our matrix to the identity matrix just by doing row switches. So when I row switch, we change determinant by a minus 1. So we have the determinant of the identity, which is 1, times a sequence of minus 1s. So it's going to be minus 1 to a power or plus or minus 1. Now, the matrices have determinant plus or minus 1, so we should check our example with S3. There, the identity in the 2-3 cycles have matrices with determinant plus 1. The 2 cycles have matrices with determinant minus 1. That means determinant of the matrix agrees with the sign function. That'll hold in general. So sign of a permutation is equal to the determinant of the matrix of the permutation. The way we show this, we recall the recursive definition for sign. Then we show that determinant of the matrix agrees with the defining conditions. Now, what we would want to show, sign of the identity is equal to 1, sign of any 2 cycle is minus 1, and then we have the multiplicative property. Sign of a product is equal to the product of the signs. So we show these instead using this definition here. Sign of the identity is equal to the determinant of the identity matrix, which is equal to 1, so that holds. If we take the sign of a 2 cycle, what are we doing? For the matrix, we're going to take the identity matrix and switch 2 columns. Now we can get back to the identity matrix by doing a single row switch. So we multiply the determinant of the identity matrix by a minus 1. That's going to be minus 1, so that holds also. For the multiplicative property, I'll let you work it out, but I'll note you only need 2 facts. First, that T is a homomorphism, and we've shown that, and that the determinant of a product of matrices is equal to the product of the determinants. So that'll show our identity here. Now with that, we could have defined the alternating groups in the following way. So the alternating group is going to consist of all permutations whose matrix has determinant equal to 1. Let's shift gears. So we have a homomorphism into invertible matrices. We can do better than that. We can get a homomorphism into the group of orthogonal matrices. Again, we won't show that that's a group, but we will show that we're landing in that group. Now, for a matrix to be orthogonal, Okay, what we're going to do, we take the transpose, we multiply by the original matrix, and we see if we get the identity matrix out. So this is the same as saying, if I take the matrix, take its transpose, it's the same as the inverse. And then we've seen that this is the same as the matrix for the inverse of the permutation. Two ways to see this. One, we just do the matrix multiplication. So if I want the kth entry of the product, we multiply as so, okay? And then the j's match up in the middle here. Now, because we're taking a transpose, that just says switch the I and the j here. So we're gonna have entry ji with entry jk. That's the same as taking a dot product when we take the sum. So you'll note the only way that this dot product is gonna be non-zero is if I is equal to k, and in that case, okay, we're lining up the zeros, the ones match up, and then the zeros keep going. So we're gonna get a 1 out. So we get either a 0 or a 1, and this just says if I is equal to k, we're getting the identity matrix out. So that shows our identity here. The quick and dirty way is just to write down your matrix, okay, for your permutation, and just consider one row or column. Okay, here we're going to consider column in the original matrix. When I transpose, that goes to a row. And you'll note the only way you can get these things to line up is if I multiply the ith row by the ith column. Then the ones land on each other. So it's going to put an entry on the diagonal. So we're going to have ones all down the diagonal, zeros everywhere else, and so we have the identity matrix. If we consider S3 again, for the permutation 1, 2, 3, we have the following matrix. If we take its transpose, that's the inverse matrix. And we note it's the matrix for 1, 3, 2, which is the inverse of 1, 2, 3. If I consider 1, 2, we get the following matrix. This matrix is equal to its own transpose and its own inverse. The inverse of 1, 2 is equal to itself, so that checks out also. Now, what do we get when we have matrices that are orthogonal? So what can we say about the matrices that go with our permutations? First, we could check our result on the determinant. That's equal to plus or minus 1. So if we have the equation, transpose of a matrix times a matrix equals the identity, I can apply determinant to both sides. Determinant of the identity is equal to 1. And then we're going to break apart this determinant here. So we have our product rule, which lets me write it as a product of determinants. Determinant of a transpose is equal to determinant of the original matrix. So I get determinant of our matrix squared. So that's going to say determinant is equal to plus or minus 1. And that checks our old result. If we consider change of basis, we have a result that says, if I have a matrix that's orthogonal, we can always find a change of basis that puts it in the following form. We're going to have blocks going down the diagonal, zeros off of it. We'll start with blocks of the form r sub theta. So what these are, 2 by 2 matrices, will be in the form cosine minus sine, sine, cosine. So these are just going to be plain rotations. When we run out of those, we'll have a block that's just an identity matrix, and then another block which is minus an identity matrix. Now, if we're willing to introduce complex numbers, then I could talk about the eigenvalues of this matrix. So they're going to be equal to, okay, they're going to be complex numbers that lie on the unit circle and the complex plane. So they can all be written in the form e to the plus minus I theta sub I, where the thetas are the thetas coming from these rotation blocks. Now we'll also have, okay, because we have our matrix able to be put in this form, that they're going to be diagonalizable over C. So we may not be able to put them in diagonal form if we insist on real numbers, but we will be able to over the complex numbers. Now, we haven't made use of the fact that S sub n is a finite group. That'll mean for a given permutation sigma, there'll be some power k that gives us the identity. If we apply the homomorphism property, we'll get that the matrix for sigma raised to the k is the identity matrix. Going to linear algebra, this means that the minimal polynomial for the matrix for sigma divides x to the k minus 1. This will give us two facts. First, the eigenvalues for the matrix for sigma are all going to be in the form, okay, the modulus of the eigenvalue raised to the kth power is equal to 1. This is going to be an improvement on our result from before. So using the orthogonal groups, we had that the eigenvalues all lived on the unit circle in the complex plane. This is a little bit better. This says every eigenvalue is a root of unity. So that means we're going to have eigenvalues of the form either 2 pi I divided by k raised to some integer power. We also have, okay, polynomial x to the k minus 1 factors completely in the linear factors over the complex numbers. So each eigenvalue is going to occur in the minimal polynomial exactly once as a root. And that's a condition for diagonalizability over the complex numbers. So that's going to confirm the result we had using the orthogonal groups. For a concrete example, let's consider S4. S4 has elements in the following form. We have the identity, we have 2, 3, and 4 cycles, and we have products of disjoint 2 cycles. We also note, we take the trace of a matrix for a permutation, that's just going to be the number of fixed labels. So that'll be the number of ones in the diagonal. Now, if I consider 2 cycle 1, 2, we have the following matrix. The characteristic polynomial is x minus 1 cubed times x plus 1. We check and we see that t squared minus the identity is 0. So the minimal polynomial is x plus 1, x minus 1. We have eigenvalues 1 with multiplicity 3 and minus 1. Determinant is equal to minus 1. Okay, so this is an odd permutation. The trace is equal to 2, and the fixed labels are going to be 3 and 4. So that checks out. If I consider 1, 2 with 3, 4, we have the following matrix. What do we have? Characteristic polynomial here is going to be x minus 1 squared, x plus 1 squared. Minimal polynomial, we still see that we have t squared minus the identity is equal to 0. Okay, note the exponent here is no mistake. This is saying that t squared is the identity. That's coming right from the group. These elements have order 2. Eigenvalues, here we're going to have 1 with multiplicity 2, minus 1 with multiplicity 2 also. Determinant's equal to 1, so this is an even permutation, and the trace is 0. So there are no labels that are fixed. For a 3 cycle, try 1, 2, 3. We have the following matrix. Characteristic polynomial is going to be x cubed minus 1 times x minus 1. Okay, if we do it in terms of blocks. For the minimal polynomial, we only need x cubed minus 1. Okay, now note we'll have t cubed minus the identity 0 to get our minimal polynomial. And again, that just comes from the order of the element in the group. Using the quadratic equation, we see the eigenvalues are going to be equal to 1 with multiplicity 2. Then we'll have minus a half plus minus square root of 3 over 2i, which is just e to the plus minus 2 pi I divided by 3. Determinant's equal to 1. Okay, we have an even permutation. Trace is equal to 1 for our one fixed label, which is 4. Finally, for a 4 cycle, try 1, 2, 3, 4. We have the matrix here. Minimal polynomial in this case is going to be x to the 4th minus 1. Okay, that's going to factor as x minus 1, x plus 1, x squared plus 1. Again, we check t to the 4th power minus the identity is equal to 0, but for no lower power. Eigenvalues are plus minus 1, plus minus I. Determinant is minus 1. Okay, remember if I have a cycle with an even number of labels, it's an odd permutation. And we have the trace of t is equal to 0. And we see that because there are no fixed labels here. So we're using all of them in this cycle. Now, one last shift in direction. We recall Cayley's theorem that says if G is a finite group, then we can embed G as a subgroup of the symmetric group S sub n, where n is the order of the group. If we combine that result with permutation matrices, okay, we can embed G as a subgroup of S sub n. Permutation matrices let us embed S sub n as a subgroup of On. We get the following theorem. Every finite group G may be realized as a subgroup of an orthogonal matrix group. So that means if I have a finite group, I could think of it as a group of matrices. This is good for two reasons. One, it lets us bring methods of linear algebra into group theory. Two, if our group's commutative, well, now the non-commutativity or non-abelianness is captured by matrix multiplication, which isn't nearly as mysterious.